Okay, so hi, I'm Adam. I work in the whalebone. That's the one you can see the whale invasion all over the place. I work as a software engineer. We write mainly in Go. As a start, I have a disclaimer. Originally, the topic was memory scavenging, but as I kind of got into writing it down, memory scavenging is it's mentioned and it's gone through only from a high level, but the topic is about memory management on the heap and it's tightly connected. So if you went specifically for this, I'm sorry. There is other talk if you want to leave, but if you want to hang out, you can stay here. All right. So, as we all know, every good story begins with a Jira ticket, and every Jira ticket needs a very motivated developer who is ready to tackle a ticket. In this case, that was me, and that was the ticket. If we strip it down into the requirements, basically the business guys need to move some data from one pile to another, so we need to get our shovels and start shoveling. How will we do that? We will create an API endpoint. That endpoint will read some file. It will be JSON-L file, line by line. It will apply some business logic for filtering the lines, and then it will upload the whole content of the file into some API server, whatever. Important specification is that the files are always around 30 megabytes. It's never higher. So it's pretty straightforward. Let's just go briefly through how we will do it. First of all, we need to start the server. I chose Echo for that because I'm used to it. We register some endpoint on the run path, and we assign it to some handler, and we start the server. The handler is called the run batch, and the run batch function has a read file. Not sure if you can see it, but it's pretty simple. I can explain it quickly. So we just open the file, we scan it with the Buffer scanner, line by line. We apply the business logic here, filter out some lines, and then we put it into a big struct batch into the line slice, and we return the whole batch from the function, and then we upload it to some server. That's the gist of it. This function is important because it's the one which is most memory heavy, and that's what we will be dealing with, basically. Okay, so I implemented. It was pretty straightforward, as I said, and I got to the deployment. One interesting thing during deployment is to set the resources limits to the application or the container. I expected the memory to be hovering around 30 megabytes because the file has usually 30 megabytes plus some change, some memory for the program to run. So as a professional developer, I tripled the amount and rounded up to 100 megabytes just to be sure. And I deployed it as a responsible developer. I deployed it only to dev environment. And I fired some requests. From the business point of view, it seems to be working fine. But then I checked the Grafana and the memory consumption graph, and I was a bit surprised. So what's happening here? We have this line in the middle is the memory request. This is basically guaranteed to the pod or the container that it will have the memory available. Then there is the limit. This is not a guaranteed space, but in our environment, it's usually free. And if it goes up, it just gets killed by out of memory. So we started the program here, and I fired the request, and immediately I can see that the memory consumption went to something around 65 megabytes, something like that. So that's the first thing I did not expect at all. And the second thing is that the request took like a couple of milliseconds, and the memory is being used for something around 4 or 5 minutes. Okay, so what's happening? As a professional developer, I looked at the code again, trying basically a bunch of random different fixes. I played with some buffers and some fancy JSON parsing library, expecting that I made some mistake and that I am actually allocating the memory for the file twice, right? So I tried all that, nothing helped. So I decided to take a bit more systematic approach. And there was a tool I knew about, and that's the profiler of the Go. This profiler can do a number of different things. We are interested in profiling the heap. It will tell you some information about how the memory is used by your program. It's also pretty straightforward to add. You import the pprof package, you register another endpoint where you want the handler to work. In our case, it's a heap, and then you just use the handler from the package to handle that. When you visit the endpoint, it will download the file, which is not readable by the human eye, unless you are really nerdy. So you need to put it into the Go tool, and it will give you some information about how it's used. In my case, I use the switch top, which will tell you which functions are using the most memory. So there it is. It claims that it's using 30 megabytes. I expected that before, like originally. Then there was 60, now there is 30. So I am very confused now, and I don't know what's happening. So Profiler did not rescue me. Basically, I had to take a very desperate step and start reading the documentation of the Go, and that took me to the waters of the garbage collection and the tools which can be used to monitor how the garbage collector works. As Go devs, we know that we don't really have to allocate or free the memory ourselves. So I always knew it was there. I kind of knew what it's doing, but I never really delved deeper until now. And I found that there is another tool from the Go which can tell you what is the garbage collector doing. It's the GC trace. You can set it with the environment variable go debug, and it will print some lines to the standard error output. Each line tracks the one garbage collection cycle, and it tells you stuff about memory, CPU, some Go routines, processors, and stuff. We, in our case, care only about the memory. So I took the two information and I made a small program to somehow visualize it. And as we can see, the garbage collector cares about two things. That's the heap goal and the live heap. Heap goal is the higher one, the black one. Live heap is the red one. And okay, so this seems that the heap goal kind of corresponds to the memory requested from the container point of view, the first graph we saw, and that the live heap is actually what the profiler reported as used memory, right? So I get a bit calmer. Seems that people know about this and that it's kind of supposed how it's working how it's supposed to, but I still don't fully understand. If we check the time here, how it went, the program started somewhere around here, then I fired the request, so there is a big allocation. This is the 30 megabytes, 60 megabytes, let's say. Then, after approximately 2 minutes, the live heap went down, but the goal went up for some reason. And in another 2 minutes, both went practically to zero. Not really, but let's say. Come on. Ah, cool. Yeah, that's what I just described, so it's fine. Alongside this, I found the Holy Grail, and that's this formula. This is a formula that the garbage collector uses to calculate the live heap and the used or the heap goal. So what's happening here? It takes the target heap memory is the heap goal. It takes the live heap size from the previous garbage collector cycle. It then sums again live heap size with GC roots. GC roots is let's say a variable in this formula that represents the references to the objects which garbage collector is supposed to free. And then there is some environment variable GoGC /100. The GoGC is by default 100. So if we simplify this, we can remove the GC roots because it's not significant in our case, and we get 1 here. So the total heap memory is more or less twice the live heap memory. Okay, it's starting to make sense, at least for me. If we go back, one thing, or we can see that it works as the formula suggested. At this point of time, we requested around 30 megabytes, that's the live heap, and around double that, that's the heap goal. What actually also here, this is not just one garbage collector cycle, it's like 10 or 20 of them, but they all happen in half a second, so it cannot be seen. But what happens then is that it seems that the garbage collector doesn't do anything for 2 minutes, and after 2 minutes, it frees the live heap, and it actually grows the heap size. Why is that? If we check the formula again, the live heap is taken from the previous cycle. So the previous cycle was here, and that's the highest live heap amount so far. So it actually grew it a little bit based on the live heap from the previous cycle. Then another 2 minutes pass, and the last live heap is, let's say, 0, so it drops to, let's say, 0. Okay, so there was the variable GoGC, which is seems that it can affect the counts pretty lot. So let's try what happens. What if we set it to 0? That would mean that the live heap should equal to the target heap, more or less. So if we run it with that and we check the graph again, we can see indeed the heap goal is just a little above the live heap. Then in the next cycle, after 2 minutes, the live heap goes down. The heap size stays the same because it takes the live heap from here and then it falls down again. So that seems pretty cool. It seems that we can adjust the memory usage by just one environment variable. Of course, this is not for free. There is always a trade-off. If we compare the memory usages and the CPU usages with different values for the variable, we see that basically the difference between 100 and 0 is half the memory usage, but double the CPU cost. That makes sense because the garbage collector needs to work much harder to retain the memory as low as possible. So it just frees stuff all the time and it takes more CPU to do that. Okay, so did our problem solve? First of all, there was double the size of the memory usage. That was kind of explained, and now it's expected. Let's say we can also lower it down if we want to with the variable. And then there is this retaining the memory for around 4 minutes or something like that. The garbage collector is triggered whenever you try to allocate something from the heap. So in 1 second, it can be triggered like 20, 40 times. That's each counting as one cycle. But then when you don't do anything with the program, it doesn't have anything to do. So the cycle is not triggered. And for that, there is a go routine in the background, which is running every 2 minutes. And that just triggers the garbage collector again. So after 2 minutes, it frees the live heap, usually, if you don't do anything. And after another 2 minutes, it frees also the memory which is taken from the operating system and is reported by the pod as used. And after that, it goes down. Right here, we can see the window or the graph takes longer. I sent something around 50 consecutive requests, and we can see, or I know, that after each request, the garbage collector is triggered earlier, right? Because I sent another request, and the memory is freed instantaneously and allocated again. So it just prolongs the window after the last request, but if you actually do something with the program, it will free the memory and it will work as expected. Okay, so I think the two main problems are resolved, so we know what's happening, that's fine. And now the obligatory, how does the memory scavenging come into play here? So the memory scavenger is a piece of code in the runtime environment of Go, and it's actually responsible for returning the memory back to the operating system. This is the garbage collector itself doesn't do it. He uses this scavenger, which acts as like a gateway between the virtual memory and the bytes which are used within the garbage collector context. and it translates it into the physical pages, and maps it into the physical memory. There are two of them. One is synchronous and one is asynchronous. The synchronous is triggered each time before the another allocation by the garbage collector happens. So before the allocation happens, the scavenger checks if he can free up some memory or if he should free up some memory. And after that, the garbage collector can continue to allocate. There is also a asynchronous one, which runs in the background as expected. There is the formula for when it runs is not that straightforward. It changes the pace based on the heap goals given by the garbage collector. And of course, there is also scav trace, which you can set again into the go debug env, and it will print out what the scavenger is actually doing. Okay, also one mention for another tool I would like you to know is the memstats in the runtime package. Basically, you can track or monitor all of the heaps attributes in that, how much is allocated, how much is released back, etc. But don't use it in production. It stops the world every time you try to read the memstats. It's a similar thing that the garbage collector does. It just pauses everything until it's resolved. I forgot one thing about the Go GC env, which tells the garbage collector how much memory it should keep in spare. And that is, you can turn it off, and you will turn off the garbage collector, so don't do that as well, because your pod will get out of memory killed too. Another reason, important, I'll scroll back a little bit, why this is happening, that it allocates the more memory than it needs, is that for the garbage collector, suddenly there is like a request for 30 megabytes. So he's like, okay, oh boy, he's gonna do it again next time, right? He will need another 30 megabytes. That's what he expects. So he preemptively allocates double the memory by default, just to be sure that you don't surprise him the next round. And if you then reuse the memory, it frees it up and allocates it again, and the total heap goal just stays the same. Okay, so some takeaways from the presentation. The memory which is reported as used by the operating system is not the same as the application is actually using. I hope the difference is kind of clear now, also that why the garbage collector does it. And Go manages the memory for us, but I think we should still kind of at least a little bit know what's happening under the hood, so that you don't get up like me spending 2 days like pulling your hair out. Go has a bunch of different tools for all kinds of monitoring of these things. I think I mentioned these three. That's the profiler, the memstats, and Go debug. So don't be lazy and use them. It will tell you more or less what's happening, hopefully. And if the use case calls for it, you can use the Go GC environment variable to balance out the CPU and the memory usage in your programs, which is pretty cool. You can also set it to higher than 100, and it will proportionally request that much memory, right? So you can just request the whole memory of the container and keep it there and never free it. As for the resources for this, I recommend you to go to the official Go documentations. It's pretty well written, and one thing I like about Go is that you can debug the source code within your program. Basically, you can click through all the stuff and see what's happening. So I recommend to do that as well. And I believe that is it. I guess we are going to the questions now.
I was curious whether the runtime memstats somehow directly correlate with the alive and target that you mentioned.
I will repeat the question. So you are asking if the memstats are correlating. You don't mean if I saw it? Sorry?
If it's like map, whether like the alive heap is the allocated in the memstats or something like that.
Okay, I'll repeat. So basically the question is if the memstat package correlates with the garbage collector's reported heap usage. Yes, most of the things are actually taken out of the garbage collector controller. The memstat has some things on top of that, like how much memory it gave back, and some calculations on top of it. So there is some extra stuff.
Okay.
Mm-hmm.
Is there any way how to tell Go to pre-allocate some amount of memory? For example, you have that 13 megabytes, so tell them your heap should not go under 30 megabytes, just not to garbage collect every time.
So the question is if you can pre-allocate some amount of memory when the program starts so that it stays the same even if you don't use it, basically. I believe that's doable via the sync pools, if I'm not mistaken. Oh, that will be topic of the next presentation.
I know the answer for this.
Okay.
Yeah, it's possible via memory ballast. Some like maybe etcd and others, they introduce a memory ballast, which is basically, hey, 200 megabytes or something. How it works, it's that you'll take a slice, a byte slice, do it or make it that size, and don't use it. And it's kind of a, hey, don't go under this. Like, I might need that memory, and that way you basically persuade a garbage collector that you need at least that memory. So it could be that this way.
Isn't it doing the same thing as the sync pools, actually?
Sync pools might get
garbage
collector.
Okay. Thanks. All right, that seems like that's it. So thank you all for the attention. Enjoy your lunch and your day, and see you around.